Alright, hello class. Today we're going to be talking about section 3.2, or at least that's where we are starting. And that is on derivative rules. Okay, and derivative rules, well, the whole motivation here is to try and get away from the limit definition of the derivative. Because say we have to find, say we want to calculate the equation of a tangent line. Right, and so the first step is usually calculating the derivative, right? Evaluating the derivative, finding f prime of x, and that takes a long time when you're using the limit definition. So that is our main motivation here, is to try and go beyond or move past the limit definition. Mainly because it takes too long, right? And also the idea is that you can use some rules and tricks and ideas that we know about the derivative and the limit and come up with ways that we can find patterns or little properties that we can use instead of having to go to the limit definition every single time we want to take derivatives. But you should always remember the limit definition, because there are cases where you will have to go back to it, where your rules won't actually help you. And just knowing what a derivative is in terms of limits is really what separates somebody who actually knows calculus and somebody who can just, say, manipulate little tricks. Okay, so before we start, what I want to introduce here is something called Leibniz's notation. Now, I'll be using this a lot, okay? And it's just another way to talk about the derivative, right? So we already know the f prime, right? If we have a function f of x is equal to something, we take its derivative, that's f prime of x. Another way to say that is if we have the derivative of y, or if we want to take the derivative of y equals f of x. Okay? Y is equal to some expression of x. And with respect to x, what we say is that dy over dx is equal to f prime of x. That's the derivative. Dy over dx. The derivative of y with respect to x. And where this comes from is basically we know that f prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. Another way you could write this is the limit as, say, b goes to a of f of b minus f of a all over b minus a. But the whole point of this here is what I'm trying to get at is that this is essentially a change in y over a change in x, right? This is a change in y's, a change in x, and so this is technically a slope. That's something to keep in mind here, is that the derivative is nothing more than a slope, it's nothing more than a fraction, and specifically a delta y over delta x when we take the limit as delta x goes to 0. And as delta x goes to 0, so does delta y. And we say that this is dy over dx. Okay. So, what d really stands for, so if delta is change in, right, change in y, change in x, then d actually stands for what we would call an infinitesimal change in. It's what infinitesimal change in, if I'm spelling that right. That's the word that Isaac Newton coined to talk about derivatives, to talk about limits, to talk about a change so small that you're talking about the difference between 1 and 1.00000000001, like an infinitesimal change. And I really don't think I spelled that right. But as Newton is considered the father of calculus, Leibniz, on the other hand, we use his notation far more than Newton's. His notation was quite good. Okay, so we're going to be using this notation, and it's mainly for convenience, because if I want to say find the derivative and all that, what I can actually say is I could use d over dx as an operator, because I could say, hey, take the derivative of f of x, and that would give me f prime of x. Another nice thing about it is it reminds us that the derivative is a fraction. Right? It is a very special fraction, but nothing more than a fraction. Just a change in y over a change in x, but just on a very, very minuscule scale. All right, so in class, we already came up with a couple of rules on your last worksheet. So the first one that we came up with, using the limit definition enough times to finally find a pattern, is what we call the power rule. So what the power rule says is that the derivative with respect to x of x to a power is equal to the power times x to the power minus 1. Okay, so it's p times x to the p minus 1. All right, and this is, even though we only looked at it for just a small number of possibilities, we looked at basically whole numbers up to 4. We looked at the fraction 1/2. We looked at -1. It does actually work for any real number p. Okay, it will be a little later before we can show why that is true, but it will work for just about anything. Okay, and we saw a couple of examples of that before, but essentially, if I wanted to take the derivative with respect to x of x to the 10th, well, I would end up getting 10x to the 9th. Okay. If I wanted to take the derivative with respect to x, and here's why this notation is really handy, because I don't have to write an f of x equals. I could just crank out the derivative all in one line. Okay, but let's say the derivative of x to the, I don't know, let's say 1/5 power is going to be 1/5. You bring the power down, x to the 1/5 minus 1. And this is when you need to start getting used to fractional arithmetic. But when you subtract 1 from 1/5, that's 1/5 minus 5/5. So that's going to be -4/5. Now, you could, move that down underneath the fraction if you want. But as far as I'm concerned, you can pretty much stop right here. And how about the derivative with respect to x of x to the -3? Well, that's going to end up being -3x to the -4. And again, let me write this out as -3 minus 1 up here. A lot of people mess this up and just go straight to -2, but remember, with your negative powers, that you're still subtracting by 1. Okay? And again, you could move this underneath the fraction if you like. Personally, you could just stop right here as far as I'm concerned. All right, don't stop here. Don't just leave it as -1. All right, don't wimp out on your fraction arithmetic. Just go ahead and crank it out. Okay, so that's the power rule. The next thing we established in class was the exponential rule. So let's go ahead and look at that. All right, so the exponential rule basically says, okay, that the derivative with respect to x of e to the x is itself. This is probably the easiest derivative rule we have. Okay, well, we're starting with the easiest ones. I mean, power rule is pretty easy, but this one, I mean, if you don't remember this one, that's bad news. And we can actually extend this. Okay, we can extend this to e to anything, right? So I'll say a constant times x. Okay. And a constant times x, if we have that in the exponent, we actually end up getting that the derivative of that is that constant c times e to the cx. Okay. What that means, so this is the rule here. What that means is if I say, for instance, take the derivative of e to the 5x, okay, that ends up being 5e to the 5x. Right, fair enough. If I take the derivative with respect to x of e to the x over 2, well, that's essentially the derivative with respect to x of e to the 1/2 times x. So that will actually be 1/2 e to the 1/2 times x. Notice what I did here. I kept that derivative sign until I actually calculated the derivative. If I take a step to simplify, I'm not going to try and take the derivative at the same time. This is just like limit signs. They have to stay there until you actually calculate the derivative. All right, one rule we need before we can really start cranking out derivatives that would, be a little more difficult is what we call the constant multiplication rule. So say I know the derivative of f. Okay, so that's what we know. We know the derivative of f. And we want to calculate the derivative with respect to x of c times f of x, where c is a constant. Well, this is actually very simple. It works just like it did with limits. Okay. What we can do is take the constant outside, and so it will be the constant times the derivative of f. So it will be c times f prime of x. Right? Very, very easy property. It basically comes from the property that we know from limits, where the limit property is that if we have a constant sitting on the outside, we can move the limit around the constant. We can do the same thing here. So for example, if I want to take the derivative with respect to x of 5x squared, well, that 5 is just going to come along for the ride. Okay, so this will be 5 times the derivative with respect to x of x squared. So this is 5 times the derivative of x squared by the power rule is 2x to the 1. So the whole thing comes out to be 10x. Okay. All right, the next rule we need to start calculating more limits, or excuse me, more derivatives, is the sum rule. So if, let's say we know the derivatives of, let's say, f of x and g of x. Right, we know both f prime and g prime, and I want the derivative with respect to x of f of x plus g of x. This will also be a minus g of x if you want. You can just think of g as being some negative function. The sum rule basically says that this is just going to be, well, I can actually distribute this derivative sign. So it's just going to be the derivative with respect to x of f of x plus the derivative with respect to x of g of x. In other words, this is just going to be f prime of x plus g prime of x. Okay. And since I feel like I should show, actually let me leave that there for just a second. I feel like I should show where at least one of these comes from. So we'll actually look at an explanation using limits of where this comes from. All right, let's let s of x be f of x plus g of x. And I'm going to calculate s prime of x. Okay. S for sum. So the derivative of the sum is going to be the limit as x goes, as h goes to 0 of s of x plus h minus s of x all over h. Okay, so that's going to be the limit as h goes to 0 of, well, s of x plus h, well, s is just f plus g, so that's going to be f of x plus h plus g of x plus h. And then this minus s of x, well, that will be minus f minus g. All right, so minus f of x minus g of x all over h. Now I'm going to group my g's and my f's together. All right, so I'll get the limit as h goes to 0 of f of x plus h minus f of x, then plus g of x plus h minus g of x all over h. And then the last thing I'm going to do, well, almost the last thing I'm going to do, is split this fraction up, right? Because now I have the limit as h goes to 0 of f of x plus h minus f of x all over h plus g of x plus h minus g of x all over h. Now these should look pretty similar. In fact, I have basically the limit of a sum, and we can use that limit rule that we have that says that I can distribute that limit across sums if I want. So this will be the limit as h goes to 0 of f of x plus h minus f of x all over h plus the limit as h goes to 0 of g of x plus h minus g of x all over h. Now these two things should look familiar, right? This should look like f prime, and this should look like g prime. In fact, that's exactly what we get, right? So we end up with, this is equal to f prime of x plus g prime of x. So that's the explanation for the sum rule, right? We got what we expected. I'm not going to do it for the constant multiplication rule, but it works exactly the same way. You can crank that out on your own if you're interested, but I figured you should at least see one of these to convince yourself that these derivative rules we're looking at actually just come from limit rules, right? So that's the big takeaway here, is that derivatives are limits, right? So a lot of the rules, not all of the rules, but a lot of the rules will carry over. Right, so here is that sum rule again. And where that comes in handy, right, is if I want to take, let's say we want to take the derivative with respect to x of, I don't know, let's say x squared plus x cubed. Right? If you had to go to the limit definition to do this one, it would be a pretty big pain. I mean, you all had to go through just x squared all by itself, and you had to go through x cubed all by itself. Then you'd have to put it together with the same steps, and it'd be a huge nightmare. But with the sum rule, what it says is that basically this derivative is just going to be the sum of the derivatives. Right? It will be derivative x squared plus the derivative of x cubed. Okay? And the derivative of x squared we know is 2x, and the derivative of x cubed is 3x squared, and we're done. So much faster than the limit definition, right? Okay, and we can throw in the idea with the constants as well. Let's say I want to take the derivative with respect to x of 5x cubed plus, actually let's do minus 9x to the 100th. Now imagine doing this one using the limit definition. Imagine expanding that one out, right? How long that would take. Well, now we know it's just the sum of the derivatives. And it'll be the derivative of this first guy, 5x cubed, minus the derivative of this second guy, 9x to the 100th. Right? So I'm going to write this out step by step here. This 5x cubed, that derivative will be 5 times the derivative of x cubed, okay, which would be 3x squared, minus 9, because those constants just come along for the ride, times the derivative of x to the 100th, which will be 100x to the 99th. All right, so this actually ends up being 15x squared minus 900x to the 99th. Right? So, most people actually, when they see this, will jump straight to this. I'm just showing every little rule I can here. I didn't write every single step, but I wrote most of them. But once you get more familiar, you can jump straight to here. All right, now there's one last rule to talk about before we start looking at some more examples. And that is basically that the derivative of a constant, okay, just all by its lonesome, is equal to 0. And there are quite a few ways to talk about this, quite a few explanations for why that's true. Okay. One, if we go to the limit definition, so say we have some function k of x, k for constant, right? And it's equal to c. And if you prefer, we could actually say it's equal to something like 5, just to help us out. And if I go to the limit definition, right, I have that the limit as h goes to 0, right, the derivative is the limit as h goes to 0 of k of x plus h minus k of x all over h. Okay. Now, the thing is, k of x plus h, well, no matter what I plug into k, it just gives me 5. So k plus h is going to be 5, okay, and k of x is going to be 5. So I basically have 5 minus 5 over h. So this is the limit as h goes to 0 of 0 over h, and that's 0. Another way to think about it is you can always think of a constant term, a constant, as actually being an x to the 0 sitting right next to it, right? And a polynomial, you have the powers going down from n to whatever, and the constant term you can always think of as x to the 0. And if you use the power rule on that, you would get 0. Oh, you'd have the constant come along for the ride. And then you'd have the derivative of x to the 0, which using the power rule would be 0 times x to the 0 minus 1. And the whole thing will come out to be 0. So, the neat thing about that is, no matter what the constant looks like, right? So if I want to take the derivative of 5, it's 0. Or if I want to take the derivative of 5 to the 100,000th power, that's still a 0. Okay, if I wanted to take the derivative with respect to x of e to the 20th, now you might get confused and think that that's e to the 20th, but that's a constant. E to the 20th is a constant, so that's 0. Right? The derivative with respect to x of pi, well, that will also be 0, so on and so forth. Okay. So that one's also, in fact, all the rules we've looked at today are pretty easy. So if you're having a lot of trouble with these, you really need to see me, because they're going to get a lot more difficult. This is just the beginning. But if you don't have these down, you are going to have a hell of a time with the next few sections, because we're going to build on this. Right? We're going to build on what we're looking at right now. So if you don't have the power rule, the exponential rule, this constant rule, and these basic rules down, you are going to be in a lot of trouble. Okay, so let's crank out some examples. Okay, let's start with something simple. Let's say I have y equals 5x to the 6th minus 3x cubed plus 2. And I want to take the derivative. Now when I do that, what I'm going to write is, say, dy over dx. Okay, and crank this out. So the constant is going to come along for the ride. So this will be 5 times the derivative of x to the 6th. So that will be 6x to the 5th. Okay, then minus 3 times the derivative of x cubed, which will be 3x squared, plus the derivative of 2, which is going to be 0. And I'm writing that out just so we're all clear that the constant of, or the derivative of a constant is 0. And again, I don't typically write this like this. I usually just go straight to the next step, which is going to be 30x to the 5th minus 9x squared, and we're done. Okay, not too shabby. Let's try another one. Let's say I have y is equal to 7x squared, okay, minus 3 times x to the, let's say, 1/3, okay, plus 5x to the negative, let's say, 4 power, plus let's say this, no, let's do pi to the 99th power. Okay, so when I want to go to take the derivative, right, dy over dx, well, derivative of 7x squared is going to be 14x. I'm skipping that step of the constant coming along for the ride, but remember the 2 comes out front, multiplies by the 7. Then it's going to be, I'll actually write it out this time, it'll be 3 times, when I use the power rule here, will be 1/3 x to the 1/3 minus 1. Okay, and again, I will eventually stop writing things like this, but for now, I don't think it's all that bad. Then plus 5 times negative 4 times x to the negative 4 minus 1. Again, I'm just writing it out here just to, extra practice with the negative exponents. Then what's the derivative of pi to the 99th? Well, that's just going to be 0. Right? It's going to be 0 because pi to the 99th is a constant. There's no x's. Okay, so I'm going to get 14x minus, well, 3 times 1/3, that's just going to be 1, so this will be x. And 1/3 minus 1, well, 1 is 3/3, and that's going to be negative 2/3. Right, and leave these as fractions. Don't give me like 0.6666 as an exponent. It just looks tacky. Right, and then it will be minus 20 x to the negative 5. And we're done. All right, let's look at another example. All right, next example, it's going to be e to the 3x plus the square root of x plus 7 over x squared plus the cubed root of 17. Now, e to the 3x, that one's a pretty simple one to do. Its derivative is just going to be itself times that constant there, 3. But these others, at the moment, they don't look like they fall into the pattern that we know, right? The only pattern that we know at the moment, other than e to the constant times x, is an x to a power, right? That's basically what we know right now, power rule. Well, these don't look like that, like they satisfy this pattern just yet, but we can actually rewrite them so that they do, right? So I'm going to rewrite this problem. I'm going to leave e to the 3x alone, okay? And then the square root, that's the same thing as saying x to the 1/2 power, okay? And then x, or 7 over x squared, that's the same thing as saying 7x to the negative 2. So any fractions, you're going to want to move up to be a negative exponent, and any roots, you're going to move to be a fractional exponent, and then we're going to have that cubed root of 17 there. We're not going to change that. We could write that as 17 to the 1/3 power, but there's no need to do that because, well, it's a constant and its derivative is going to be 0, of course. Now, look at what I've done here. I have taken the time to simplify this, and I've done it all in one step. Okay, this is what you're supposed to do. If you need to simplify, do it in an entire step. Have a step for simplification, then have a step for the derivative. Okay? So now I can say that the derivative, dy over dx, is going to be 3 e to the 3x, right, from the exponential rule, plus, using the power rule, I get 1/2 x to the 1/2 minus 1. I'll go ahead and write that out like that this time. Then it will be minus 14 x to the negative 3 plus 0. And let me go ahead and simplify this. Right, this will be 1/2 x. 1/2 minus 1, of course, is negative 1/2. Minus 14 x to the negative 3. Now for this test in particular, this is okay with me. You can stop right here. All right. But for your online homework and, you know, if you're checking your answers in the book and all that, you're probably going to want to simplify. But for me, on, say, the test, the worksheets, in-class stuff, stop right there. Just take the derivative and move on. The whole point of all these rules and all these tricks is to make it so we can take derivatives much faster. And so I don't want you wasting time simplifying. In fact, if you simplify incorrectly, if I see some bad algebra, I'll take off for that, versus if you just stop right here and move on. But if you do want to check your answers in the book, you're working on the online stuff, you're going to move those negative exponents into the denominator. Okay. And then the last thing you can do is change that 1/2 power to be a square root. Right, so we have e to the 3 e to the 3x plus 1 over 2 times the square root of x minus 14 over x cubed. And that's it. But again, this one works too. So this trick that we just did, these two tricks, right? If I have a root of x, if I want to take the derivative of that, I'm going to write it as x to the 1 over n. And if I have x in a fraction like this, say 1 over x to the p, I want to write that as x to the negative p so that I can use the power rule. Right? So that's really what we're trying to do here, is rewrite things so that we can use the power rule. So let's look at some more examples. But I do want to mention that these two tricks we are going to use a lot. I mean, a lot. So get familiar with them. If you've forgotten them from algebra, remember them and don't forget them again, because they're going to keep coming up. Okay, here's another example. Say we have the cubed root of x squared minus 2 over x cubed plus 100 e to the x over 4 plus e squared plus x to the pi. Alright, so first I'm going to go through and simplify things. So remember, that's the first thing you're going to want to do. Don't start taking derivatives of things that you can, and simplify in the same step. It's extremely confusing. I'm saying this as a mathematician who has to read and grade students' work. When I see that, it's very confusing, because I'll see you started taking the derivative and then you simplified what you started with, and it's not the derivative. Once you say y prime or f prime or dy dx, everything that follows has to be the derivative. If you need to simplify, simplify first. So here we're going to simplify first, then differentiate. Okay, so cubed root of x squared. Well, the cubed root is raising this to the 1/3 power. So this is essentially x to the 2/3. Okay. Minus, okay, so 2 over x cubed, that's going to be 2x to the negative 3. Right? Then we'll have, well, this one doesn't change much. That's still 100 e to the x over 4. Then plus e squared, doesn't change much. And x to the pi, it's not really going to change much. Okay. Now we're going to take the derivative. Right? So dy over dx. Right? So this will be 2/3 x to the 2/3 minus 1. So I'll go ahead and write that out again. Again, eventually I'm going to stop doing that, but 2/3 minus 1 is just going to be negative 1/3. Right? Then this is going to be plus 6x to the negative 4. Okay. Then plus 100, then the derivative of e to the x over 4. One thing I could have done up here at the simplification step is rewritten this as 1/4 x, if that would help. I'm going to write this like this here, 1/4 e to the 1/4 x. Then the derivative of e squared is 0, since that's a constant. And what about the derivative of x to the pi? Well, it doesn't matter what this constant is. I'm going to bring it down. It's pi. And I'm going to raise it to the pi minus 1. Okay. And so I'll simplify some of this stuff now. This is going to be 2/3 x to the negative 1/3. Right. Plus 6x to the negative 4 plus 100 divided by 4, that will be 25 e to the 1/4 x. And then pi x to the pi minus 1, that's about as simplified as that gets. So we are pretty much done. Okay. And that is that. All right, up next, here's an example that on first glance doesn't actually look like we can do things with this. But again, if you need to simplify, and that's always your first step, is to simplify. All right, so step 1, we're going to simplify. Now, those of you who have taken calculus before know that you can use the product rule here, but don't just start going through taking derivatives. You've got to actually multiply this through first. Okay, you can't. Oh, the only rule we have is for sums, right? And this is not a sum, this is a product. So let's expand this out, multiply it out, and then we can use the power rule. So simplify, then use the power rule. Okay, so that's what we're going to do. So first I'll distribute this x squared across, and I'll get, so x squared, so I'll get x to the fourth minus 2x cubed plus 5x squared, okay, then plus 3x cubed minus 6x squared, and plus 15x. Okay, and now I'll go ahead and combine my like terms. I've got x to the fourth, negative 2x cubed plus 3x cubed, so that's plus x cubed. Then I have 5x squared minus 6x squared, so that's minus x squared. And then a plus 15x. And we're good to go, right? We've now rewritten this problem. We've expanded out and got it as just a sum of x's to powers. That's exactly what we need. So now we can take the derivative, which is that f prime of x is going to be 4x cubed plus 3x squared minus 2x plus 15, and we're done. Okay, next example. Let's say I have f of x is equal to x to the 10th plus 30x to the 6th minus 7x. And once again, this is a problem of that this does not fall under the pattern that we recognize. All we can actually do is, sorry about that, is take derivatives of sums of things, and we have a quotient, a fraction of things. Okay? Now, don't just think that you can go through and take the derivative of the top over the derivative of the bottom. It doesn't work that way. Okay? So here, I'll go ahead and simplify. One thing I can actually do is use algebra to break this fraction up. So that's one thing I'll do is this is x to the 10th over x to the 5th plus 30x to the 6th over x to the 5th minus 7x over x to the 5th. Okay, so this ends up being x to the 5th plus 30x minus 7 over x to the 4th. Okay. So from here, okay, what we're going to do is take one more step of simplification. Because over x to the 4th will be x to the negative 4. Right? And now we have it as a sum of powers. Alright, so this, when I take the derivative, so f prime of x will end up being 5x to the 4th plus 30 plus 7 times negative 4, or negative 7 times negative 4. So that will be 28x to the negative 5th, and that is that. Okay. Now, let's say you actually did go ahead with just taking the derivative of the top over the derivative of the bottom. You would end up getting 10x to the 9th plus 180x to the 5th minus 7 all over 4x to the, 5x to the 4th. Now, when you actually distribute this across, right, if you broke this down like we did over here, you're not going to get the same thing, right? Already that first term is going to be 10x to the 9th over 5x to the 4th, which ends up being x to the 5th, which is not the first term here. Okay, the next term, right, which is 180x to the 5th, over x to the 4th, 5x to the 4th, excuse me, right, that ends up being plus 36x, and then we have negative 7 over 5x to the 4th. That doesn't really simplify at all, and these two are not the same, right? These two are not the same. So which one is actually correct? Well, it's actually this one. Okay, so one thing I want to go ahead and mention right now beforehand, and we'll talk about it more in 3.3, it comes from this question of what is the derivative of f of x times g of x and f of x over g of x, right? And I will go ahead and tell you that the derivative with respect to x of f of x times g of x is not f prime of x times g prime of x. And the derivative with respect to x of f of x over g of x is not f of x or f prime of x over g prime of x. Okay, it's definitely not. Okay. So the answer to this question we'll actually look at in 3.3, the next section. Those of you who have seen calculus before, you know exactly what the answer is, hopefully. And but for now, if you see a fraction like this, or you see a product like this, you're going to use algebra to simplify it down to where you can actually use the power rule on everything. And that's the answer that is going to be correct. Okay? All right, the last thing I really want to talk about, well, one of the last things I want to talk about is how now applications that we've been doing get so much easier, right? That we can actually use these rules to help us out. So let's say I want to find the equation of the line tangent to f of x equals 4x minus x squared at x equals 1. So remember, when we go to find the equation of the tangent line, we need two things, right? We need a point and we need the slope. And where do we get the slope? Well, we get that from the derivative. Okay, so here's about what this graph looks like, and we're looking for the equation of the tangent line at this point here. Right, so about right here. Okay, so we have the point. It's the point 1 comma f of 1. We've been through this before. So f of 1 is going to be, I plug 1 into here, that will be 4 minus 1. So it's the point 1 comma 3. Okay, so we have the point. Point check. Now we need the slope. Okay, and the slope, well, we go to the derivative. So the slope is going to be given to us by the derivative. So first I'm just going to crank out the derivative. So f prime of x is going to be 4 minus 2x. Okay, and we're looking at the slope, well, specifically, so So actually, let me write this instead, that the derivative is f prime of x, but the slope is going to be f prime of 1. Now I write it like this first because it's better to find f prime of x, then plug in 1, than trying to do it all at once. So f prime of 1 is going to be 4 minus 2, so that's 2. All right, so now we're going to put it in this formula. Y equals mx plus b. We have our point, 1, 3, so I get 3 is equal to the slope, which is 2, times the x value, which is 1, and then we solve for b. So it's just a matter of moving 2 over to get that b is equal to 1. So this equation here of this line is y equals, the slope was 2, x plus 1, which looks about right. My graph isn't exactly to scale, but it looks about what we would expect. Okay, another thing that becomes super easy is the problem we looked at earlier. This isn't exactly the same, but very similar, is that, let's say a rock is dropped from 500 feet. Its height above the ground at t seconds is given by this function here. S of t is equal to 500 minus 16t squared. It's given to us in feet. Okay, right, this is the initial height. This is the gravity term. So we're going to find the instantaneous velocity of s of t as a function of t. Okay, well, the instantaneous velocity, well, the interesting thing about how derivatives work is, remember, the derivative of the position, right, is going to be the velocity. In other words, if I made a function v of t that I want to be my velocity function, all I've got to do is take the derivative of the position, which is s of t. So s prime of t, well, from here, s prime of t is going to be super easy. It's the constant 500, so 0. Okay, I'll go ahead and write that out. Minus 16 times t squared, so the derivative of t squared is just 2t, so this will be minus 32t. And this is in feet per second. Okay, so that function that it's asking for, right, the velocity is negative 32t. So now I can find the velocity at whatever time I want. Right, so at 1 second, the velocity is just going to be negative 32 feet per second. At 2 seconds, the velocity is going to be negative 64 feet per second. Okay, let's say at a half second, v of 0.5 is going to be negative 16 feet per second. What about at 0 seconds? V of 0 is 0 feet per second. Does that make sense? Well, the rock is just dropped. It has no initial velocity. In other words, this is the initial velocity, and mathematically, the number we got actually makes sense for that. Okay, so that brings us to a really important concept of calculus, is that, and it's carried on into physics, it's that the derivative of the position, which we usually call s of t, is the velocity, v of t. And we can actually take it a step further and say that the derivative with respect to t of the velocity is acceleration. Right? That's the rate of change of the rate of change. Fair enough? So this would be, say, in feet. S of t is in feet. v of t is in feet per second, and acceleration, which we call a of t, is going to be in feet per second squared. Okay, and there's more examples that we'll look at later on, but I just wanted to introduce this here, that now that we have these rules, we can find the instantaneous rate of change, or the instantaneous velocity of a function really, really quickly, right? I think we had one in your on your worksheet that was something like negative 16t squared plus, what was it, 32t plus 49, something like that. And if you remember, it took a lot of work to actually break that all down and figure that out. But with the rules you've just learned, the velocity, if we wanted it at whatever second we had, we would just take the derivative and get negative 32t plus 32. And bam, you can figure out whichever one you want by plugging in the values. Okay, so that's about all I want to talk about right now from 3.2. I'll talk to you next time. Cheers.